Welcome to G-Fun Facts Online. Imagine standing on a vast, open plain, gazing up at the sky. To the naked eye, the space above is simply empty air. But from the perspective of an energy engineer, the sky is an invisible, roaring ocean of untapped power. For decades, humanity has attempted to harvest this energy by building increasingly massive steel towers, anchoring them deep into the earth, and hoping the wind blows hard enough near the ground. We clear forests, pour thousands of tons of concrete, and use specially designed megacranes just to put these traditional turbines in place. But what if we did not have to wait for the wind to come down to us? What if we could send our power plants up into the sky to meet the wind exactly where it is the strongest? Today, we are diving deep into the cutting-edge frontier of airborne wind energy systems, or AWS, and specifically focusing on the revolutionary development of high-altitude aerostats, which are essentially megawatt-class wind power airships. Blending aerospace engineering, advanced composite materials, and next-generation renewable technology, these floating power banks in the sky are preparing to fundamentally rewrite the rules of global energy generation. To truly understand why some of the smartest engineers in the world are attaching wind turbines to giant helium-filled blimps, we first need to take a close look at the physics of wind itself. Ground-based wind turbines, despite their massive size and impressive engineering, suffer from a very significant limitation, and that limitation is the Earth itself. The friction caused by trees, mountains, buildings, and even the flat ground surface creates massive amounts of turbulence. This friction drastically slows down the wind in what physicists call the lower boundary layer of the atmosphere. Because of this, ground-based turbines often sit idle on calm days. However, as you ascend past this boundary layer, the wind profile changes dramatically. When you reach altitudes of 500 to 2,000 meters, which is roughly 1,600 to 6,500 feet, the winds are completely unobstructed. They are significantly faster, highly consistent, and flow with a smooth laminar predictability that ground-level turbines can only dream of. Here is where the mathematical physics becomes practically magical. The kinetic energy available in the wind is proportional to the cube of the wind speed. This is a crucial point. It means that if you double the wind speed by moving your turbine from ground level up to 2,000 meters, the available energy does not just double. It increases by a factor of 8. 2 times 2 times 2. Some advanced studies indicate that high-altitude wind power can generate several times, or even dozens of times, more electricity than traditional ground-based wind power when comparing similar swept areas. By accessing this high-altitude jet stream, a floating wind power airship can achieve a capacity factor, which is the percentage of time it generates its maximum rated power, that actually rivals nuclear or coal baseload plants. This effectively solves the notorious intermittency problem of traditional renewable energy, where power drops off when the sun sets or the surface wind dies down. Now, let us break down the anatomy of a megawatt-class wind power airship. At first glance, a high-altitude aerostat looks like a futuristic vehicle pulled straight from the pages of a science fiction novel. But every single inch of its design is a masterclass in functional engineering. The system generally consists of 4 main components. First is the buoyant envelope, or the airship itself. Unlike a traditional blimp designed for moving cargo or passengers, a wind power aerostat is essentially a massive inflatable lifting body, designed to stay perfectly stationary in gale-force winds. The outer shell is crafted from highly advanced, lightweight, weather-resistant composite materials that prevent the lifting gas from leaking. Usually this gas is helium, though highly stable hydrogen-nitrogen mixes have also been studied to reduce costs. Some of the most advanced designs feature a hollow, annular, or donut-like shape. This is not just for aesthetics. This hollow inner space acts as an aerodynamic duct, capturing the wind from all sides and funneling a concentrated, high-velocity stream of air directly into the turbine blades. The second major component is the turbine array. Instead of using a single, massive rotor that weighs tons and creates immense rotational stress, modern megawatt-class airships use a distributed array of smaller, highly efficient turbines. These generators are often constructed from ultralight carbon fiber. By distributing the generation across multiple turbines, sometimes up to 12 individual rotors mounted within the airship's central aerodynamic duct, the system perfectly balances torque. This distributed design dramatically reduces structural stress on the airframe and maximizes the extraction of kinetic energy from the funneled wind. The third component is the tether system, which is arguably the most critical and complex engineering marvel of the entire operation. It acts as an umbilical cord of power. The tether serves two very distinct but equally important purposes. It acts as a high-strength anchor to keep the massive airship from blowing away, and it serves as the conductive conduit that transmits the generated high-voltage electricity down to the Earth. To achieve this, these tethers are typically constructed with an inner core of ultra-high molecular weight polyethylene, such as Dyneema or Kevlar, which provides immense tensile strength that rivals steel at a fraction of the weight. This super strong core is then wrapped around conductive elements, usually lightweight aluminum or copper composites, to send power to the grid, along with integrated fiber optic cables to relay real-time telemetry, weather data, and control signals back and forth. The fourth and final component is the ground station. Located at the base of the tether, this mobile unit houses a heavy-duty, highly advanced winch system. This winch can autonomously deploy the airship into the sky, automatically adjusting its altitude in real time to hunt for the absolute optimal wind speeds. If a severe superstorm or a hurricane approaches, the winch automatically reels the multi-million-dollar airship back down to the safety of the ground. The ground station also contains all the necessary power conditioning equipment, ensuring the raw electricity sent down the tether is converted into perfectly stable, grid-compliant alternating current before it is integrated into the local microgrid or utility network. The journey from a theoretical concept to a megawatt-class reality has been marked by bold pioneers and, more recently, staggering leaps in scale. In the early 2010s, an MIT spin-off named Altyros Energies proved that this concept was actually viable. They developed the buoyant airborne turbine, or the BAT, an automated, helium-filled cylindrical aerostat with a single turbine suspended in the center. In 2014, Altyros successfully tested the BAT in the harsh conditions of Maine and Alaska, deploying it at altitudes of up to 1,000 feet. While the BAT was a relatively small system, generating enough power for a few dozen homes, it was a vital proof of concept. It proved that high-altitude aerostats could survive severe weather, enduring up to 45-mile-per-hour winds, and successfully transmit steady, affordable electricity to remote, off-grid locations. Fast forward to early 2026, and the technology has achieved a monumental, industry-shaking milestone. Beijing-based Linyi Yunchuan Energy Technology successfully tested the world's first megawatt-level airborne wind power system, designated as the S2000 Stratosphere Airborne Wind Energy System, or SAWES. The scale of the S2000 is simply breathtaking. Measuring 60 meters long, 40 meters wide, and 40 meters high, the S2000 has a volume of nearly 20,000 cubic meters. To picture this, imagine a colossal floating sports stadium. During its maiden flight in China's Sichuan province, the S2000 ascended to an altitude of 2,000 meters, or about 6,560 feet. At this incredible height, hovering a full kilometer above the tip of the Burj Khalifa, the airship deployed its 12 integrated turbines. It successfully generated and fed 385 kilowatt-hours of electricity directly into the power grid during its initial test. With a maximum rated capacity of 3 megawatts, the S2000 has taken airborne wind energy completely out of the realm of small experimental prototypes and firmly established it as a utility-scale commercial viability. You might be wondering, why go through the immense engineering trouble of building floating power plants when we already have thousands of traditional wind turbines? The advantages of high-altitude aerostats are incredibly disruptive to the current global energy landscape. First is logistical simplicity and rapid deployment. Building a traditional wind turbine is a massive, incredibly expensive civil engineering project. It requires clearing acres of land, pouring thousands of tons of concrete for a deep foundation, and using specialized, oversized trucks and megacranes to assemble the massive tower and blades, often requiring roads to be widened or built from scratch just to transport the parts. In stark contrast, An Aerostat system like the S2000 can be neatly packed into standard shipping containers. Once it arrives on site, it requires virtually no permanent groundwork. You simply unroll the envelope, inflate it with helium, activate the autonomous winch, and the power plant literally lifts itself into the sky. A complete Megawatt-Class system can be fully operational in a matter of days, rather than the months or years required for traditional wind farms. Second is zero visual and noise pollution. Ground-based turbines face heavy, constant opposition from local communities due to the low-frequency noise they generate and the obstruction of natural, scenic skylines. A wind power airship operating at 2,000 meters is practically invisible to the naked eye from the ground, looking like nothing more than a tiny speck if you can see it at all. It is also completely inaudible from the surface. This opens up the incredible possibility of deploying high-capacity renewable energy systems directly above heavily populated urban centers, without inciting the classic not-in-my-backyard protests. Third is the minimal ecological footprint. Ground turbines require large swaths of land and, unfortunately, can pose serious collision risks to low-flying local bird and bat populations. The Aerostat requires only the physical footprint of its ground station winch, which is smaller than a typical parking lot. This preserves valuable agricultural land and dense forests, while the system itself operates smoothly well above the flight paths of almost all avian wildlife. This incredible flexibility opens up entirely new, real-world applications for renewable energy. Consider disaster relief and emergency response. When devastating hurricanes, earthquakes, or tsunamis wipe out regional power grids, the immediate lack of electricity severely hampers rescue operations, water purification, and emergency medical procedures. Currently, disaster relief heavily relies on trucking in heavy, noisy diesel generators and trying to maintain constant, expensive fuel supply lines through destroyed roads. An airborne wind system acts as a rapid response power bank in the sky. It can be flown or trucked into a disaster zone, deployed in hours, and float high above the devastation to immediately beam megawatts of clean, reliable, life-saving power down to emergency hospitals and command centers. Then there are off-grid and remote outposts. For remote island communities, polar research stations, and isolated mining camps, connecting to a national grid is physically and economically impossible. These remote locations rely entirely on imported diesel fuel, resulting in exorbitant electricity costs that can sometimes exceed $1 per kilowatt hour, not to mention the heavy carbon emissions. High-altitude aerostats offer an economically viable, highly stable alternative, providing continuous baseload power without the need for complex permanent infrastructure or constant fuel shipments. Furthermore, these systems offer urban grid supplementation. Because they leave no visual footprint and require almost zero land, these systems can be safely tethered near the perimeters of massive megacities. By tapping into the powerful stratosphere, they can feed immense amounts of electricity directly into power-hungry urban grids, effectively creating a layered, three-dimensional energy supply that does not compete for precious real estate. However, despite the incredible, almost utopian promise of this technology, turning the sky into a global power grid comes with unique, highly complex challenges that aerospace engineers and government regulators are actively working to solve. First is helium containment and material science. Helium is an incredibly tiny, slippery molecule. It is the second lightest element in the universe, and it is highly prone to escaping through the microscopic pores of almost any material. For an aerostat to be economically viable, it must remain aloft for many months at a time, without requiring constant, wildly expensive helium top-offs. Developers are investing heavily in high-performance, multi-layered polymer laminates to create near-perfect gas barriers that can withstand extreme UV radiation and freezing temperatures without degrading. Second is tether dynamics and aerodynamic drag. A physical cable stretching 2,000 meters into the sky is subject to immense aerodynamic drag and a complex physical phenomenon known as vortex-induced vibration. This is the exact same physical force that makes a guitar string hum or a car antenna whip back and forth in a strong breeze. The tether must be aerodynamically stable and perfectly tensioned to prevent snapping under constant stress, while remaining light enough so that its own weight does not drag the blimp back down to Earth. Finally, there is the massive hurdle of airspace integration. Tethering a giant blimp miles into the sky inherently introduces a massive, invisible, high-tension cable straight into active, navigable airspace. Widespread global adoption of airborne wind energy systems will require unprecedented, close coordination with major aviation authorities like the FAA in the United States and EASA in Europe. Ground stations will need to be strictly equipped with aviation transponders, high-visibility radar reflectors, and restricted airspace digital geofencing to ensure the absolute safety of commercial airliners, cargo flights, and private aircraft. The successful flight of Megawatt-Class wind power airships like the S-2000 marks a truly pivotal moment in the history of human energy generation. We are no longer strictly bound by the friction and geographical limitations of the Earth's surface. By intelligently utilizing advanced aerospace materials, cutting-edge distributed turbine design, and the brilliantly simple elegance of natural buoyancy, we are finally unlocking the massive, raging rivers of wind that constantly circle our globe. As global manufacturing scales up, with pioneering companies already establishing massive production bases capable of churning out millions of linear feet of these high-performance envelope materials, we are inching closer to a future where clean, infinite, highly reliable energy is pulled directly out of the sky. In the near future, the silent sentinels of the stratosphere will not just be weather balloons or orbital satellites. They will be the very engines powering our world below, operating invisibly and silently to fuel the next generation of human progress. Thank you for joining us on this deep dive on G Fun Facts Online.